To understand how humanity currently plans to speak with extraterrestrial intelligence, we have to look at the Voyager Golden Record. The instructions on this artifact operate under a set of highly specific assumptions. They assume that whoever finds it will be a distant, static target. They assume we have infinite time to wait for a reply. And they assume there is zero immediate threat to Earth. We built our entire search infrastructure around these passive, zero-threat assumptions. The Arecibo radio telescope, for example, was designed to sit quietly and listen to deep space, hoping to catch a faint signal from light years away. But a distant static target is the best-case scenario. If an interstellar object enters our solar system on a high-speed impact trajectory, those assumptions collapse. Legacy detection protocols offer no guidance for a mobile, time-compressed, and potentially hostile target bearing down on our position. Passively broadcasting to the stars is a luxury of distance. An inbound ISO demands a strict, mathematically rigorous strategic response. This requirement reveals the information communication paradox. The first half of the paradox dictates that as an ISO's threat level rises, the strategic necessity to initiate contact increases at the exact same rate. The second half of the paradox creates the conflict. As that threat level rises, the probability of any communication actually succeeding inversely drops toward zero. In time-compressed scenarios, this relationship creates a tactical conflict. The indicators that demand a response are the exact factors suggesting the response will fail. To navigate this conflict, defense analysts developed the Threat Communication Viability Index, or TCVI. The TCVI is a deterministic algorithm. It is designed to override subjective assessments and replace them with objective calculation. It identifies the exact point where a governing body must abandon strategic silence and begin active diplomatic signaling. It translates the existential dread of alien first contact into a cold, objective systems engineering problem. This equation represents the complete Threat Communication Viability Index. It mathematically balances the physical proximity of an approaching threat against the logical feasibility of sending a message. We start with the top half of the equation, the numerator, which defines the threat vector. The first variable is the object's lobe scale rating, which ranks the object's anomalous, non-natural characteristics from a baseline of 1 up to a maximum of 10. That rating is divided by the square root of the remaining days until the object's closest approach or impact. This graph illustrates why we use the square root. At long distances, the dampening effect creates a flat curve that prevents premature alerts while the object is still months away. But as those remaining days compress into weeks or hours, the curve shifts. The threat score climbs sharply as the time variable approaches zero. The numerator mathematically enforces patience when we have the luxury of time, and extreme urgency when we do not. Now look at the bottom half of the equation, the denominator. This section acts as a constraint, factoring in the realities of signal processing. The first constraint is the communication window. This measures the hard transit time required for a radio signal to cross space, plus the days required on Earth for decoding a response. Then we multiply that window by the success probability. The model assumes cross-species communication begins at an optimistic baseline of 50%, but that probability suffers a compounding 11% penalty for every confirmed hostile indicator observed. These indicators include active communication jamming, sudden trajectory shifts toward Earth, or the detection of directed energy beams. Each penalty shrinks the denominator, mathematically representing the collapse of diplomatic viability as the success probability plummets. As the object acts more hostile, the equation acknowledges that the window for diplomatic resolution is narrowing, significantly restricting the final viability score. Let's run a live test of the model. Imagine an ISO 7 object, 150 days away, displaying only one hostile indicator. Plugging those variables into the model yields a low TCVI score of 0.17. Under the strategic communication protocols, a 0.17 dictates continued strategic silence. At this score, the risk of exposing Earth's technological baseline outweighs any potential diplomatic value. We watch and we wait. Now we pivot to a high threat scenario, an ISO 8 object, 45 days out, displaying 3 separate hostile indicators. The compounding penalties cause our success probability to drop to 7%. Because of the compressed timeline and high threat, the final TCVI calculation spikes to 3.41. A score of 3.41 exceeds the critical threshold, triggering the mandate for immediate communication. By relying on this mathematical threshold, Earth's defense systems can flip from passive observation to active engagement instantly, bypassing deliberative delay. This raises the operational question. Once the index breaches 1.5 and mandates communication, what exactly do we transmit? We abandon human language and greetings entirely. Instead, we rely on legacy xenolinguistic frameworks like the Lincos model. The Lincos framework bridges extreme cognitive gaps by using raw binary pulses to communicate mathematical concepts like basic arithmetic. Today, that framework is utilized in the Peaceful People Protocol, specifying the data payload for high-threat scenarios. The protocol dictates transmitting universal constants, such as pi or the golden ratio. We then convert those constants into harmonic frequency ratios to demonstrate predictable, organized intelligence. This specific mathematical payload proves our rationality to an inbound object without inadvertently signaling military aggression or panicked distress. This chart displays the full spectrum of TCVI thresholds, ranging from observe up to existential defense. But the formula has a primary mathematical limitation, the 300-day limit. Because of the dampening effect in the numerator, the math compresses too tightly for objects further out than 300 days, rendering the recommendations useless. The framework also fails to provide a coordinated response if Earth encounters multiple uncoordinated ISOs simultaneously. Then there is the ultimate edge case, the possibility that the ISO is an automated von Neumann probe. If a probe operates on predetermined programming with no sensory apparatus to receive our signals, the probability of successful communication is 0. The TCVI is a highly specialized tool built for a specific range of engagement. Beyond these temporal and situational limits, the model provides no actionable data. Attempting to communicate under high-threat conditions is a low-probability gamble. Transmitting any signal inherently exposes our location and our technological baseline to a confirmed threat. But we have to weigh that risk against the alternative of total inaction while a hostile object approaches. The strategic communication protocols formalize this final calculation. When time is limited on an interstellar threat, taking a mathematically verified low-probability action is strategically superior to accepting the risks of silence.